A scientific theory is a well-substantiated explanation of some aspect of the natural world that is acquired through the scientific method and repeatedly tested and confirmed through observation and experimentation. As with most forms of scientific knowledge, scientific theories are inductive in nature and aim for predictive power and explanatory capability. The strength of a scientific theory is related to the diversity of phenomena it can explain, and to its elegance and simplicity. See Occam's razor. As additional scientific evidence is gathered, a scientific theory may be rejected or modified if it does not fit the new empirical findings. In such circumstances, a more accurate theory is then desired. In certain cases, the less accurate unmodified scientific theory can still be treated as a theory if it is useful as an approximation under specific conditions. Scientific theories are testable and make falsifiable predictions. They describe the causal elements responsible for a particular natural phenomenon, and are used to explain and predict aspects of the physical universe or specific areas of inquiry. Scientists use theories as a foundation to gain further scientific knowledge, as well as to accomplish goals such as inventing technology or curing disease. Scientific theories are the most reliable, rigorous, and comprehensive form of scientific knowledge. This is significantly different from the common usage of the word theory, which implies that something is a conjecture, hypothesis, or guess. Characteristics of theories. Essential criteria. The defining characteristic of all scientific knowledge, including theories, is the ability to make falsifiable or testable predictions. The relevance and specificity of those predictions determine how potentially useful the theory is. A would-be theory that makes no observable predictions is not a scientific theory at all. Predictions not sufficiently specific to be tested are similarly not useful. In both cases, the term theory is not applicable. A body of descriptions of knowledge is usually only called a theory if it fulfills the following criteria. It makes falsifiable predictions with consistent accuracy across a broad area of scientific inquiry. It is well supported by many independent strands of evidence, rather than a single foundation. This ensures that it is probably a good approximation, if not completely correct. It is consistent with pre-existing experimental results and at least as accurate in its predictions as are any pre-existing theories. It can be subjected to minor adaptations to account for new data that do not fit it perfectly, as they are discovered, thus increasing its predictive capability over time. It is among the most parsimonious explanations, economical in the use of proposed entities or explanatory steps. The first three criteria are the most important. Theories considered scientific meet at least most of the criteria, but ideally all of them. This is true of such established theories as special and general relativity, quantum mechanics, plate tectonics, the modern evolutionary synthesis, etc. Definitions from scientific organizations. The United States National Academy of Sciences defines scientific theories as follows. The formal scientific definition of theory is quite different from the everyday meaning of the word. It refers to a comprehensive explanation of some aspect of nature that is supported by a vast body of evidence. Many scientific theories are so well established that no new evidence is likely to alter them substantially. For example, no new evidence will demonstrate that the Earth does not orbit around the Sun, or that living things are not made of cells, that matter is not composed of atoms, or that the surface of the Earth is not divided into solid plates that have moved over geological timescales. One of the most useful properties of scientific theories is that they can be used to make predictions about natural events or phenomena that have not yet been observed. From the American Association for the Advancement of Science. A scientific theory is a well-substantiated explanation of some aspect of the natural world, based on a body of facts that have been repeatedly confirmed through observation and experiment. Such fact-supported theories are not guesses, but reliable accounts of the real world. The theory of biological evolution is more than just a theory, it is as factual an explanation of the universe as the atomic theory of matter or the germ theory of disease. Our understanding of gravity is still a work in progress, but the phenomenon of gravity, like evolution, is an accepted fact. Note that the term theory would not be appropriate for describing untested but intricate hypotheses or even scientific models. Formation of theories. The scientific method involves the proposal and testing of hypotheses. By deriving predictions from the hypotheses about the results of future experiments, then performing those experiments to see whether the predictions are valid. This provides evidence either for or against the hypothesis. When enough experimental results have been gathered in a particular area of inquiry, scientists may propose an explanatory framework that accounts for as many of these as possible. This explanation is also tested, and if it fulfills the necessary criteria, then the explanation becomes a theory. This can take many years, as it can be difficult or complicated to gather sufficient evidence. Once all of the criteria have been met, it will be widely accepted by scientists as the best available explanation of at least some phenomena. It will have made predictions of phenomena that previous theories could not explain or could not predict accurately, and it will have resisted attempts at falsification. The strength of the evidence is evaluated by the scientific community, and the most important experiments will have been replicated by multiple independent groups. Theories do not have to be perfectly accurate to be scientifically useful. For example, the predictions made by classical mechanics are known to be inaccurate in the relativistic realm, but they are almost exactly correct at the comparatively low velocities of common human experience. In chemistry, there are many acid-base theories providing highly divergent explanations of the underlying nature of acidic and basic compounds, but they are very useful for predicting their chemical behavior. Like all knowledge in science, no theory can ever be completely certain, since it is possible that future experiments might conflict with the theory's predictions. However, theories supported by the scientific consensus have the highest level of certainty of any scientific knowledge, for example, that all objects are subject to gravity or that life on Earth evolved from a common ancestor. Acceptance of a theory does not require that all of its major predictions be tested, if it is already supported by sufficiently strong evidence. For example, certain tests may be unfeasible or technically difficult. As a result, theories may make predictions that have not yet been confirmed or proven incorrect. In this case, the predicted results may be described informally with the term theoretical. These predictions can be tested at a later time, and if they are incorrect, this may lead to revision or rejection of the theory. Modification and improvement of theories. If experimental results contrary to a theory's predictions are observed, scientists first evaluate whether the experimental design was sound, and if so they confirm the results by independent replication. A search for potential improvements to the theory then begins. Solutions may require minor or major changes to the theory, or none at all if a satisfactory explanation is found within the theory's existing framework. Over time, as successive modifications build on top of each other, theories consistently improve and greater predictive accuracy is achieved. Since each new version of a theory must have more predictive and explanatory power than the last, scientific knowledge consistently becomes more accurate over time. If modifications to the theory or other explanations seem to be insufficient to account for the new results, then a new theory may be required. Since scientific knowledge is usually durable, this occurs much less commonly than modification. Furthermore, until such a theory is proposed and accepted, the previous theory will be retained. This is because it is still the best available explanation for many other phenomena, as verified by its predictive power in other contexts. For example, it was known in 1859 that the observed perihelion precession of Mercury violated Newtonian mechanics. but the theory remained the best explanation available until relativity was supported by sufficient evidence. Also, while new theories may be proposed by a single person or by many, the cycle of modifications eventually incorporates contributions from many different scientists. After the changes, the accepted theory will explain more phenomena and have greater predictive power. This new explanation will then be open to further replacement for modification. If a theory does not require modification despite repeated tests, this implies that the theory is very accurate. This also means that accepted theories continue to accumulate evidence over time, and the length of time that a theory remains accepted often indicates the strength of its supporting evidence. Unification of theories. In some cases, two or more theories may be replaced by a single theory which explains the previous theories as approximations or special cases, analogous to the way a theory is a unifying explanation for many confirmed hypotheses. This is referred to as unification of theories. For example, electricity and magnetism are now known to be two aspects of the same phenomenon, referred to as electromagnetism. When the predictions of different theories appear to contradict each other, this is also resolved by either further evidence or unification. For example, physical theories in the 19th century implied that the sun could not have been burning long enough to allow certain geological changes as well as the evolution of life. This was resolved by the discovery of nuclear fusion, the main energy source of the sun. Contradictions can also be explained as the result of theories approximating more fundamental phenomena. For example, atomic theory is an approximation of quantum mechanics. Current theories describe three separate fundamental phenomena of which all other theories are approximations. The potential unification of these is sometimes called the theory of everything. Example: relativity. In 1905, Albert Einstein published the principle of special relativity, which soon became a theory. Special relativity predictively aligned the Newtonian principle of Galilean invariance, also termed Galilean relativity, with the electromagnetic field. By omitting from special relativity the luminiferous ether, Einstein stated time dilation and length contraction to be expected by an observer measuring an object in relative motion inertial, that is, an object exhibiting constant velocity, which is speed with direction, when measured by its observer, and thereby duplicated the Lorentz transformation and the Lorentz contraction that had been inserted into electrodynamic theory as dynamical consequences of the ether's properties hypothesized to resolve experimental riddles. Elegant, special relativity yielded its own consequences, such as the equivalence of mass and energy transforming into one another and the resolution of the paradox that an excitation of the electromagnetic field could be viewed in one reference frame as electricity, but in another as magnetism. Einstein sought to generalize the invariance principle to all reference frames, whether inertial or accelerating. Rejecting Newtonian gravitation, a central force acting instantly at a distance, Einstein presumed a gravitational field. In 1907, Einstein's equivalence principle inferred that a free fall within a uniform gravitational field is equivalent to inertial motion. By extending special relativity's effects into three dimensions, length contraction became space contraction in general relativity, whose 4D spacetime is the gravitational field that local alters geometrically and sets all local objects' pathways. And even massless energy exerts gravitational motion on local objects by curving the geometrical surface of 4D spacetime. Yet unless vast, the relativistic effects of energy, whether by speed or mass, in the vicinity, where space is contracted and time is slowed, are negligible when merely predicting motion. Although general relativity has embraced the more explanatory theory via scientific realism, Newton's theory remains successful as merely a predictive theory via instrumentalism. To calculate trajectories, engineers and NASA still uses Newton's equations, simpler to operate. Theories and laws. Both scientific laws and scientific theories are produced from the scientific method through the formation and testing of hypotheses, and can predict the behavior of the natural world. Both are typically well supported by observations and/or experimental evidence. However, scientific laws are descriptive accounts of how nature will behave under certain conditions. Scientific theories are broader in scope, and give overarching explanations of how nature works and why it exhibits certain characteristics. Theories are supported by evidence from many different sources, and may contain one or several laws. A common misconception is that scientific theories are rudimentary ideas that will eventually graduate into scientific laws when enough data and evidence have been accumulated. A theory does not change into a scientific law with the accumulation of new or better evidence. A theory will always remain a theory, a law will always remain a law. A theory is valid as long as there is no evidence to dispute it. Therefore, theories can be disproven. Theories and laws are also distinct from hypotheses. Unlike hypotheses, theories and laws may be simply referred to as scientific fact. However, in science, theories are different from facts even when they are well supported. For example, evolution is both a theory and a fact.